Hey, welcome to week 6. If you look at the board behind me, a little bit of a history lesson going along with our Martian learning today. We're learning about life science by using a couple of clips, a couple of selected scenes from the movie The Martian. And last time when we left off, we saw Matt Damon, Mark Watney, the character in the movie, Matt Damon being the actor, blow himself up accidentally. Not completely blow himself up, but he had an accident there in the hab because he was trying to make water. He was trying to use hydrogen gas, combine it with a little bit of oxygen, and when he gets the ratio a little bit off, boom, we get this big explosion. So I start off with, of course, Led Zeppelin, because why not? It's Led Zeppelin. If you're not familiar with Led Zeppelin, may I suggest going on, checking out their greatest hits album, and you'll probably come across this particular picture behind me, which is kind of badly drawn on the board, but it's a picture from what they used as their cover art, which was the Hindenburg. It was a Graf Zeppelin, a Zeppelin that was flying in 1937 into the United States from Germany. And a little bit of a history background here because we talk a little bit about World War II. We need to know a tiny bit about it in this class. This particular Zeppelin was used by the Nazis in World War II as propaganda. Now, it's hard to imagine a worse regime, a worse totalitarian government than Nazi Germany. If you think about Germany nowadays, very, very different in terms of the Republic of Germany. Think about it like this: if you are in the United States, you could be a Democrat, you could be a Republican, you could be a Libertarian, you could be the Peace and Freedom Party, you could be the Kermit the Frog Party, you could be a member of whatever political party you want to be. If you were in Germany in around 1935, 36, you could be in the Nazi Party, or that was it. There was no other choice. All the other parties, if you will, were outlawed. And if you look at one of the things that happened in the United States in the 1930s, especially towards the later part of the 30s, the United States started to have a clue, started to get an idea that, hey, you know what, we're probably going to run into conflict with the government of Nazi Germany. So they stopped selling Nazi Germany helium. Now, as you probably know, and this is where I need the whiteboard for just a second, as you probably know, in a party balloon, we have helium. If you have, for example, a balloon like this, and I've got my microphone spun around, if you have a balloon like this, you've got He in them, because as you have helium in a party balloon, you go to a birthday party, you have balloons on the cake, and if you have helium that gets a little bit too close to one of these candles on the cake, it's not going to blow up. The balloon itself might, pop, and then the helium, one He atom, is going to float gently away into space, and that's it. If, however, you've got a balloon filled with hydrogen, two hydrogen atoms stuck together. Remember, hydrogen is diatomic, fancy way of saying it likes to travel in pairs. So you've got H2 in your balloon, you've got an H and an H, and it gets too close to one of these party balloons. You'd be blowing up your party guests right and left if you filled it with hydrogen. Not a great thing to have in a balloon. When you check out the cover art that Led Zeppelin used on this particular Zeppelin that blew up in 1937, the Nazis would use this thing as propaganda. For example, during the 1936 Berlin Olympics, and if you're not familiar with that, look it up. Jesse Owens went over to, among many other athletes, but Jesse Owens went over representing the United States and ended up beating some of the athletes, which was great in terms of Hitler had this crazy idea about the master race in Nazi Germany. So it was great to see, Nazi Germany get a little bit of like, hey, there's really no such thing as a master race. It's absolutely unbelievably ridiculous. And if you look at the balloon, the blimp, bigger than a balloon, that was flying around, this thing was used, to carry the Nazi flag around. It would literally drop leaflets, not just in Berlin, but all over Germany as part of their propaganda effort. And if you look at this thing coming over to the United States, in 1937, it was filled with hydrogen. Why? Again, the United States kind of had an idea that we're going to have a conflict with this country eventually, and they stopped selling helium. The United States had pretty much a monopoly on helium at the time. Pretty much the only helium production in the world was happening right here in the United States. And you can use helium for some military purposes. So they stopped selling them helium, so the engineers said, fine, we'll make our blimp, our Graf Zeppelin, and we'll float it with hydrogen gas instead. Now, hydrogen gas it is more buoyant than helium, but It's also, as we saw in The Martian, a chemical reaction happens, and it's extraordinarily volatile. That means it can combine with oxygen readily, and it can react readily because it has electrons that it wants to give away. The long and the short of it is, in the movie, he took, and again, back to the whiteboard for just a second, he took a little bit of H2, and he took a little bit of O2, hydrogen gas, which he had left over as rocket fuel, oxygen, which in our atmosphere is put there, remember, by the chemical reaction photosynthesis. He takes those and he puts them together to make good old water, H2O. Now, look at the online notes, look at the written out notes for the balanced chemical equation here. Remember, this has to conform with our conservation laws, so we end up with the right number of atoms on each side of the equation. But the long and the short of it is, you take hydrogen gas, react it with oxygen gas, you get water. The first time he does it in the movie, it's a great illustration of a chemical reaction gone wrong. He gets the ratios a little bit off. Mark Watney, portrayed by Matt Damon there, gets a little bit off, kind of blows himself up, but he also kind of interjects a little bit there about how the Jet Propulsion Laboratory got going. So when this Zeppelin came over to the United States in 1937, we still to this day don't know what happened. Most likely somewhere there was a leak on the Zeppelin, a leak on the blimp, and it probably got sparked by some static electricity. Whatever happened, it could have been sabotage as well, we'll never know. But the point being, this really kind of infamous and famous scene of the Hindenburg crashing to the ground is a dramatic example of a chemical reaction between hydrogen and oxygen, two molecules that we're going to talk about continuously throughout the course of this class. Very, very important to know about. From there, we started talking. Oh, and of course, the new Yardbirds, when they became, before they became Led Zeppelin, or as they became Led Zeppelin, they changed their name because someone had told them. Actually, it wasn't a record producer, but it was a kind of a friend. He says, "You guys are going to go over like a lead balloon." And so kind of as a joke, they changed their name, almost as a joke, to Led Zeppelin, a lead balloon. And of course, they went on to become the most famous rock band in history. And again, if you're not familiar with Led Zeppelin, I could do a whole video on those guys, but basically, look them up, they rock. Okay, moving on, we went on to talk about our theme for this week, our 10 key terms, which are up over the other side of the board. Light. We wanted to make the point that we only see a tiny, tiny piece of the spectrum of light that's out there. For example, if you go down this way, we asked a couple students to say, hey, what did you cook today? Did you cook anything in a microwave? You used microwaves, which are close to radio waves. We can't see them, but they're there. For example, if you take out the light bulb in your microwave oven, it's still going to microwave. It's still going to cook your food using microwaves, which incidentally, what they do to cook your food is they just heat up water. Heat, we talked a little bit about heat. We're going to be talking a lot more about heat when we do our whole unit on light. In particular, when we talk about some of the birds of prey that we see around here. We talk about owls, for example. They do this amazing thing where they can see rodents. They can see the heat coming off the bodies of rodents. Rodents have very high body temperatures. And an owl, this is why they do their hunting at night. If you make an owl box, it's fantastic because it will swoop on in, pick off the rats. The rats never saw what was coming because the owls can see their body heat. That, by the way, when we get into more about habitat and species in our ecosystem, is why you never, ever, ever want to use rat poisons or anything like that, because owls, a natural predator around here, do a fantastic job of picking off the rats and the mice. And later on in this year, we're going to show how you build an owl box, how you bring in natural predators to pick off those rodents in our environment. And if you use poison, say on the rats, if a rat eats a poison, it becomes disoriented. It might be outside and they get picked off by an owl. If the owl eats it, now you've poisoned the owl. And so we want to really talk a lot about habitat in our ecosystem when we get into that. It all fits together. Radio waves. Again, radio waves, when you're listening to, say, CanBR 68, you're listening to Krupp, Kuyp, Miller, and Fleming and the Giants, hopefully win independent this year. If you listen to radio waves, you can pick it up with the radio, but we can't see radio waves. Our eyes are not tuned to pick up radio waves. Incidentally, you might remember when we did a little bit of the proof of the Big Bang, this was the part of the spectrum that gave us part of our proof of the Big Bang, the microwave background radiation. So these are the types of light that we need to know about. On the right side, the way I've drawn it here, of the spectrum, you've got ultraviolet, which I know something about. For example, I spent a little bit too much time in the sun, especially when I was in my college years, working my way through partly as a carpenter. I spent a lot of time outside in the sun. Back in those days, we really didn't think too much about sun protection. Maybe you wore a hat, but that was about it. Now, you pay for it by unfortunately, skin cancers. So you have to always be on the watch for any kind of skin cancers. Why? Ultraviolet rays can damage our DNA, particularly in our skin, and cause cancers. X-rays. X-rays are safe in small doses in terms of we use them all the time. For example, you go to the dentist, they throw a lead blanket over you and they said, oh, we're going to take your X-ray now. And they run out of the room. But no, X-rays are really, really, really safe. But again, it's a type of radiation that can cause damage to DNA. And we want to talk about those a little bit more when we do our unit on cancer. And then finally, gamma rays, good and bad here. No, they don't turn you into a giant green Hulk like in the Marvel movies, but gamma rays are usually, they're naturally occurring in space when you have high energy, for example, collisions of black holes, supernova, things like that. We also can use gamma rays to fight cancer by focusing gamma rays on a tumor. However, at the same time, if a person gets flooded with gamma rays, say from a nuclear accident or something like that, it can cause cancer, cause damage to our cells, and actually cause cells to mutate. So we wanted to talk just a tiny bit about that. Finally, light in a vacuum of space travels all at the same speed. This is going to be important later on. We're going to talk about this quite a bit. C, E equals mc squared. The C stands for the speed of light. C is a constant. It's the speed of light in a vacuum. To give us some perspective on how fast it is 186,000 miles per second, or 300,000 kilometers per second in the metric system, which we should always use. That being said, that's fast enough to go around our planet, around the Earth, about 7 times in 1 single second. So when we're talking light, we're talking tremendous speeds, but yet in The Martian, and again, how it fits into the little clips from the movie that we're checking out this week, wrapping up this week too, when they're doing their communication between Mars and Earth, they have to wait about 15 minutes for the signal to go from Mars to Earth, and then, of course, another 15 minutes for the signal to come back. When you're looking into space, you're really looking back into time, and, to hurt your brain on a Monday, when you are looking at anything, you're really looking back into time because it takes a while for the light to bounce off the object and to come in through your eyes and then, of course, be registered in your brain. These were our 10 key terms this week. I'll put these out there on the online notes. And then that little orange bar was just to remind me that this was about as far as we got in class today. I was a little bit too ambitious in far as trying to get to radioactive decay. We're going to get to that tomorrow by rolling some dice and rolling some coins and showing a little bit more about how some elements naturally decay over time. You might remember Mark Watney, Matt Damon's character in the movie, uses this to stay warm. He uses a radioactive isotope that naturally decays, that does release radiation, does release heat, and it does help keep him warm in the movie, but he does correctly point out that it's also dangerous. They have radioactive elements that, even though they decay naturally over time and we can use them as batteries, particularly in spacecraft, they do produce some radiation, which you got to watch out for, which gets us back to your first board right here, which was the main thrust of the day. The electromagnetic spectrum and ultraviolet, X-rays, and gamma rays being somewhat dangerous when it comes to electromagnetic waves that can hurt our cells, hurt our DNA, and cause things like cancer. Okay, that was the quick recap. I'll get the notes out online, and also we'll do a little video on notability, which I'm starting to like in terms of being able to point out the different things from our notes. Check out some Led Zeppelin tonight if you get a chance, and I'll catch you online and in class. Bye-bye.